Today, I'm going to be completing Part A of Homework 1 for separations. And the problem that we are posed with today is that we need to derive the Clausius-Clapeyron expression for vapor pressure only using the idea that the Gibbs free energy for a pure component system is equal for both the vapor phase and the liquid phase. Now, we're going to do this by first deriving the Gibbs free energy fundamental property relationship from, again, the idea that the Gibbs free energy for a liquid and vapor are equal in a pure component system. And going on from there, we're going to rearrange our Gibbs free energy fundamental property relationship a little bit to find our Clausius-Clapeyron. Alrighty, let's go ahead and get started with our Gibbs free energy relationship. We know that the Gibbs free energy for the liquid phase equals the Gibbs free energy for the vapor phase when our systems are at equilibrium. And what that farther means is that if we had a change in the Gibbs free energy for the liquid phase, an equal change would have to occur in the vapor phase in order to bring us back to equilibrium, meaning that dGL equals dGV. Furthermore, we know that the Gibbs energy in general equals the enthalpy minus the temperature times the entropy. And if we go ahead and differentiate this using the product rule, we get dG equals dH minus TdS minus S dt. Now we still have a little bit of a problem here. Our enthalpy here, we need to break this down a little bit more. And to do that, we're going to say that H equals the internal energy U plus P times V. Furthermore, yet again using the product rule, we can say that dH equals du plus pdV plus vdP. And yet again, we have another problem variable, our internal energy. So how are we going to break that down even further? Well, we know that du is just going to equal or change the internal heat dQ plus dW for change in work. So how are we going to explain each of these terms? Let's start with dQ. When looking at dQ, we can call a familiar expression ds equals dQ reversible over T. Now, this system here is reversible with any amount of energy put in it. It's just a pure component sealed system. So we can rearrange this a little bit to get our dQ equals TdS, which eliminates the Q variable. Moving on to our dW, our work, it's helpful to kind of look at a model of a piston. So say we have a system here at a certain volume, a certain pressure, going to here. Since our piston moved up in this case, and I'm not the best artist, but that is what happened here. This is our system doing work on the piston. And that work is defined by the volume times the pressure, which yields dW equals minus P dV, or change in volume. And the minus is here because our system is doing work on the piston. So we're getting work out. Taking these two expressions that we've just found and plugging them in for du, we can get our dH equals T ds minus P dV plus P dV plus V dP. And then subbing this into our total Gibbs energy relationship, we get dG equals T ds minus P dV plus P dV plus V dP minus T ds minus S dt. And clearly here, there's a lot of variables we can knock out. We can get rid of our TDSs, we can get rid of our PDVs, which leaves us with our final Gibbs free energy fundamental property relationship. dG equals VdP minus S dt. Now we can move on from here to find our Clausius-Clapeyron from this expression. Now that we have our fundamental property relationship for the Gibbs free energy and our previously derived dGL equals dGV, we can say the volume of the vapor phase dP minus the entropy of the vapor phase dt is going to equal the volume of our liquid phase dP minus the entropy of our liquid phase dt. And if we move this around a little bit to isolate our dP and our dt, we'll get the volume of our vapor phase minus the volume of our liquid phase dP is equal to entropy of our vapor phase minus the entropy of our liquid phase dt. Now we're still nowhere even close to the Clausius-Clapeyron expression, but there's a few key assumptions we can make here that get us very close to that expression. And the first of those is that we're going to assume that the volume of our liquid is zero. And this is simply because of the nature of the two different phases. In a system like this, at normal conditions, you're always going to have so much more volume of vapor than you are of liquid that we can typically just assume that the volume of liquid is zero. And that'll make this a lot easier moving down the line. Going on from there, this is essentially just delta S or ds. If we remember from earlier, we had an expression for ds which was Q reversible over T. Now for this system, any energy that comes in here, as we just have two components in this isolated system, all of that Q coming in is going to be the enthalpy of vaporization, because all of that energy is going to go into the phase change. It's going to be making the liquid into the vapor or the vapor condensing into liquid. So we can sub out our dQ reversible for the enthalpy vaporization over T. Enthalpy of vaporization over T. So, going on and subbing this in to our equation, we get volume of the vapor, Vp, equals enthalpy vaporization, delta V, over T. We're going to put in our delta up there. Times T. And we're starting to get pretty close to what we would consider to be our Clausius-Clapeyron, but we're going to need to sub out our VV here. And how we're going to do that is we're just going to look at the ideal gas equation. Our PV equals RT for a molar base quantities. By rearranging this a little bit, we get that V equals RT over P. So subbing this into our equation, we get RT over P dP equals delta H vap over T dt. Now, we isolate our variables. We can get 1 over P dP equals delta H vap over R times 1 over T squared dt. Now here is an expression we can integrate to get our Clausius-Clapeyron. So we're going to go ahead and take the integral from P1 to P2 over our P and the integral from T1 to T2 over our T expression. What we're going to get from this is the natural log of P2 over P1 is going to equal our delta H vap over ideal gas constant R times negative 1 over T2 minus 1 over T1. And to make this look more like Clausius-Clapeyron, I'm just going to go ahead and move our negative in front of our delta H vap. And here we have a Clausius-Clapeyron expression for the vapor pressure derived simply from the idea that the Gibbs free energy is equal for both the vapor phase and the liquid phase. Now moving on from here, we can look at the second part of our problem for part A. Now moving into question 2, part A for homework 1, we're posing the question to derive the conditions where relative volatility is constant, given a binary mixture composed of a liquid phase and a vapor phase under ideal conditions. So to do that, we're going to use both the Clausius-Clapeyron, which we derived earlier in this video, as well as a secondary equation, Raoult's law. Now, Raoult's law says that the liquid composition of one of the binary components, we'll just say I for now, times the saturation vapor pressure of that component equals the vapor composition of that component times the total pressure. Now that we have the two equations that we're really going to need to find the conditions where relative volatility is constant, we need to define what relative volatility is. And to do that, we got to start with the partition coefficient, which I'll abbreviate as PC. The partition coefficient, denoted as Ki for component I, is just the vapor phase composition divided by the liquid phase composition. And from the partition coefficient, we can also now find our relative volatility. Which, denoted by alpha, we'll say I and j, as this has to do with both of the components in our mixture. Our alpha ij is just equal to the partition coefficient for component I, Ki, divided by the partition coefficient for component j, Kj. Alrighty. And now that we have both our partition coefficient and our relative volatility defined, we can start to play around with these equations a little bit, find something a little more useful. So, looking at Raoult's law, we can see that yi over xi is simply equal to saturation vapor pressure of I over the total pressure. So we can go ahead and sub this in for our partition coefficient. Partition coefficient Ki just equals Pi sat over the total pressure, derived from Raoult's law. Furthermore, looking at our relative volatility, we can see the relative volatility also equals Pi sat over P divided by Pj sat over P. What we can see here is that we can get rid of the total pressure, defining our partition coefficient simply in terms of saturation vapor pressures. Right. And that gives us the whole story. What exactly our partition coefficient and relative volatility is. Now, we can go ahead and move on to playing with the Clausius clapeyron a little bit. So we're just going to create a Clausius for each component I and j. So for component I, the Clausius clapeyron is going to look like the natural log of Pi2 over Pi1 equals negative the enthalpy of vaporization for component I over R times 1 over T2 I is 1 over T1 I. And then we're just going to do the same for J. For our J, so natural log Pj 2 over Pj 1. So negative enthalpy of vaporization for J over R times 1 over T2J minus 1 over T1. It's a lot of writing, a lot of repeating. So what we're going to do now is something a little bit more important. we're going to split up this logarithm. Instead of writing this all out, I'm just going to erase a couple parts of this. See here, if we just subtract out these logs, we can get the natural log of P2I and the natural log of P2J is just going to equal this whole expression plus the natural log of P1I and P1J. Going on from here, we can now subtract both of these equations from each other to get one gigantic equation that we're going to be able to use to find what conditions relative volatility is constant. So, subtracting these two terms out, we get ln of P2I over P2J equals negative delta H VAP. Actually, we'll come back to that term. We're going to start with those logs. So our ln P1 I over P2 1J. Sorry, my algebra is terrible here. Then we can finally add in these terms, which will give us minus delta H I plus delta H J over R times one over shit. I have to make this a little bit simpler. One over T 2I minus 1 over T 2 1 I should say. T1I and 1 over T 1J. And this expression has our T1s, which are our initial values that were given, meaning these are constant because they're from state 1. Same with our initial pressures. So what's the term that's going to cause problems? Well, that's obviously our T2s. So, adding on to this, we've also got to add our delta H VAP I minus our delta H VAP J all over R times our R1 over T2 I minus R1 over T2J. Now, it's very important to notice that if this term goes to 0, we can knock out this entire term, leaving us with two constants from the beginning, meaning we have constant relative volatility, as this value here would be constant. And this value is our saturation vapor pressure for our I, divided by our saturation vapor pressure for our J, which if you remember up here is our equation for relative volatility. So if we've only got two constants on the right-hand side of the equation, that means that we have constant relative volatility. So how are you going to do that? Well, the easiest thing to assume is that the change in enthalpy of vaporization for I and J are very close to the same. And if they're very close to the same, that knocks out this term entirely and gives us our constant relative volatility. So, what are the conditions that give us constant relative volatility? They are assuming that the change in the enthalpy of vaporization for I and for J are the same, knocking out this term. And then, of course, all of our standard Raoult's law assumptions. We're assuming that they're an ideal liquid-vapor binary mixture, and so on. General assumptions, but this is the big assumption that makes it so that we can assume that constant relative volatility is constant. I think that just about finishes up part A of separations homework.